Tonight we're going to explore a graveyard. Not the kind you can walk through. Not the kind with stones and grass and the slow settling of the ground. The graveyard we're going to visit tonight sits so far away that the light leaving it began its journey before the Earth existed, before the sun existed, before the cloud of gas and dust that would one day become our solar system had even begun to gather itself in the dark. And when that light finally arrived, when it fell at last into the cold mirror of a telescope drifting 1,000,000 miles from home, it carried a message that no one was expecting. It told us that something out there had already lived and burned and died in the first small hour of the universe's long life. Tonight we're going to explore the discovery of galaxies that were already dead when the universe was young. Galaxies that formed their stars in a single furious burst, blazed with the light of hundreds of new suns every year, and then, before the cosmos had finished its first billion years, went cold and silent and still. Galaxies whose corpses are older than anything our best theories say should exist. Galaxies that, according to the mathematics we trusted for decades, simply could not be there. And yet there they are. Faint red smudges pinned to the deepest patches of sky we have ever photographed, waiting patiently in the dark for someone to notice that the universe had broken its own rules before the ink on those rules was dry. You don't need to follow every number tonight. You don't need to hold on to anything. Let the words move past you the way deep water moves past a boat that has stopped rowing. Somewhere in the telling, if all goes well, you'll drift off, and the galaxies will keep on being dead whether you're awake to hear about them or not. That is one of the quiet comforts of this kind of story. Nothing you do tonight will change any of it. It has all already happened, a very long time ago, in a place you will never go, and it is waiting there in the dark, finished and still, asking nothing of you at all. So settle in, let your shoulders drop away from your ears, let the weight of the day pool in the mattress beneath you and stay there. Feel the pillow give beneath the back of your head the way soft ground gives beneath a footstep, slowly, without complaint. We have a long, slow night ahead of us, and there is no hurry at all. There is nowhere we need to be. By the end of tonight, you'll understand what it means for a galaxy to die, how we learn to read the signature of that death written in a thread of ancient light, and why a handful of small red objects, no more impressive to the eye than a smudge of dust on a lens, have quietly rattled one of the most successful theories in the history of science. Now let's begin. Tonight we're going to move slowly the way you should move through any graveyard, with our voices low and our steps unhurried, stopping at each stone long enough to read the name and wonder at the story. To understand what a dead galaxy is, you first have to understand what a living one looks like, because the difference between the two is written in light, and once you know how to read it, you cannot unsee it. A living galaxy is a place where stars are still being born. Deep inside its clouds of cold gas, gravity is still doing its patient work, pulling hydrogen and helium into knots, squeezing those knots tighter and tighter until their centers grow hot enough to ignite. When a star switches on for the first time, it does not do so gently. The most massive of these newborn stars are furnaces of unimaginable violence, burning blue-white and pouring out ultraviolet light so energetic that it tears electrons free from the atoms of gas floating around them. And that torn, glowing gas has a signature. It sings. If you spread the light of a living galaxy out into its colours, the way a prism spreads sunlight into a rainbow, you do not see a smooth band. You see bright lines, sharp spikes of colour standing up out of the background like the notes of a chord. There is a line from oxygen that has been stripped of 2 of its electrons, a green line so bright and so common in young galaxies that astronomers know it the way you know the face of an old friend. There is a red line from hydrogen, the light that atoms release when a wandering electron falls back home into its lowest orbit, a line called H-alpha that glows in every place where stars are being made, glowing like a neon sign in a window, announcing to anyone who cares to look that here, right here, the universe is still busy making light. These bright lines are the sound of a galaxy that is alive. They are the emission of a place still working, still building, still ringing with the effort of creation. Now imagine most of that chord going silent. Imagine spreading out the light of a galaxy and finding that the bright lines are simply not there. The green line of ionized oxygen, gone. The red glow of hydrogen, gone. The ultraviolet scream of hot young stars, gone. Where a living galaxy shouts, "This one is quiet," and in the place of those bright emission lines, you find something else entirely. You find dark lines, absorption lines, places where light has been taken away rather than given, notches carved into the smooth flow of colour, and each of those notches is the fingerprint of a cool, old, aging star. The hydrogen that once glowed now only absorbs, leaving behind a deep ladder of dark bands called the Balmer series. The calcium in the atmospheres of old giant stars leaves its own pair of dark scars, a pair astronomers call simply H and K. This is not the spectrum of a place making new light. This is the spectrum of a place living off the fading warmth of light it made long ago. It is a spectrum with the lights turned low, a room after the party, the chairs still warm and the candles guttering. Astronomers have a word for this. They call such a galaxy quenched. It is a good word, an honest word borrowed from the world of the forge and the blacksmith. When you quench a piece of hot iron, you plunge it into water and the fire goes out of it all at once, the red glow draining away, the metal going hard and cold and still, the water hissing and then falling silent. A quenched galaxy is a galaxy whose fire has gone out. Its rate of forming new stars has dropped to nearly zero. The furnaces that once lit it have been shut off, and what remains is only the slow, inevitable cooling of the stars that were already there, aging together in the dark, growing redder and dimmer with every million years that passes, like coal settling in a grate long after the last log has burned through, giving off less and less heat, sinking slowly toward the temperature of the room around them. There is one feature of a dead galaxy's spectrum that matters more than any other, and it is worth sitting with, because it is the thing that lets us tell the living from the dead across billions of light-years of empty space. It is called the Balmer break, and it sits at a wavelength of about 4,000 angstroms, right at the edge between the ultraviolet and the visible. In a galaxy that is still making stars, that edge is soft, almost invisible, because the flood of ultraviolet light from all those young hot blue stars washes across it and fills it in. The break is weak. The light flows smoothly from the blue into the ultraviolet like water over a gentle slope, and you would hardly know the edge was there at all. But in a dead galaxy, all those hot blue stars are gone. They lived fast and they died young the way massive stars always do, exhausting themselves in a few million years and collapsing or exploding, leaving behind only the cooler, longer-lived stars that give off far less ultraviolet light. And so the break becomes a cliff. Below 4,000 angstroms the light falls away sharply, dropping into shadow, because there is almost nothing left in the galaxy hot enough to shine there. If you could stand at the edge of that spectral cliff and look down, you would be looking into the absence of every young star the galaxy used to have. The Balmer break is the spectroscopic equivalent of a fire that has gone cold. Short of that wavelength, the light simply falls away, and the steepness of that fall tells you exactly how thoroughly the fire has died. The deeper the cliff, the deader the galaxy, the longer it has been since the last new star lit up the dark. This is how we know. Not by looking at the shape of a galaxy, though the shape tells its own story. Not by measuring how bright it is, though brightness matters too. We know a galaxy is dead by spreading its light into a spectrum and reading, in the pattern of bright lines that are missing and dark lines that are present, and the sharpness of that 4,000 angstrom cliff, the unmistakable handwriting of a place that has stopped making stars. The light turns red, and it turns smooth, and it goes quiet, and that quiet is the sound of death. You could think of it as the difference between a crowded street at midday and the same street at 3 in the morning, the shops shuttered, the windows dark, The only movement a single light left on far above, burning for no one. A living galaxy is the street at noon. A dead one is the street in the small hours, hushed and cooling, remembering the day. Tonight we're going to spend our first long stretch of the dark with a single galaxy, one that speaks this language of death more clearly than almost any other we have found. Its name is not poetic. It is GS 9209, a string of characters that tells you which survey found it and where in the catalogue it sits, and nothing at all about the strangeness of what it is. It lives, from our point of view, in the direction of the constellation Fornax, the furnace, which is a coincidence too neat to leave unmentioned, because GS 9209 is a furnace that has gone out. And when astronomers pointed the great cold eye of the James Webb Space Telescope at it, and gathered its light for 5 long hours on a night in November of the year 2022, the spectrum that came back was, in the words of the man who led the work, unmistakable. What they saw was a galaxy whose light strongly resembled the light of a single kind of star, an A-type star. And to understand why that single fact made a room full of astronomers go quiet, you have to understand what an A-type star is and how long it lives. An A-type star is white and hot, brighter and more massive than our Sun, the kind of star that dominates the light of a galaxy only in the narrow window of time just after a great burst of star formation has ended. These stars burn for only a few 100 million years, which sounds like an eternity, but is barely an eye blink in the life of a universe. When a galaxy's light looks like the light of an enormous collection of A-type stars, it is telling you something very specific. It is telling you that this galaxy had a burst of star formation, an intense and glorious burst, and that the burst ended recently, so recently that the shortest-lived stars have already burned out, but the A-type stars have not yet had time to follow them into the dark. It is the light of a fire that has just gone out, the embers still glowing, the smoke still rising, the warmth still coming off the stones. It is worth slowing down and imagining as clearly as you can what it actually feels like to look at the spectrum of a galaxy like this and read its death certificate off the page. Picture a long horizontal band running from the blue on the left to the red on the right, with the brightness of the galaxy's light traced as a line rising and falling across it. In a living galaxy, that line would be jagged with bright spikes, the emission lines, each one leaping up out of the background where hot gas is glowing, and the whole left side, the blue and ultraviolet side, would be lifted high and bright by the flood of light from young stars. That is what star formation looks like when you plot it out. It looks busy. It looks loud. The eye can see the life in it. Now picture GS 9209's spectrum instead. The bright spikes are gone. Where you would expect to see the green line of ionized oxygen leaping up, there is nothing but the smooth continuum. Where you would expect the red glow of hydrogen from hot young gas, there is nothing. The line runs quietly across, no spikes, no shouting. And then, at 4,000 angstroms right at the boundary between the ultraviolet and the visible, the line does something dramatic. It drops. On the blue side of that wavelength the light is faint, and on the red side it is bright, and between them there is a step, a sudden cliff, as though someone had taken a knife to the spectrum and cut a shelf into it. That is the Balmer break, and once you know what it means, you cannot look at it without a small chill. The break exists because the hot young blue stars that would fill in the ultraviolet are gone. Only cooler, older, redder stars remain, and cooler stars give off very little blue and ultraviolet light. So the blue side of the spectrum falls away. The size of that step is a direct measure of stellar age. A small step means young stars, plenty of blue light. A large step, a deep cliff, means old stars, the blue drained out of them, the population aged and reddening. GS 9209's break was a cliff. The step was steep, and reading the steepness of that step is, quite literally, reading the age of the dead, measuring how long it has been since the last young star burned in that galaxy, all from the shape of a line on a plot. And then there are the absorption lines, the dark notches carved down into the continuum, which tell the second half of the story. Where a living galaxy has emission, bright lines rising up, a dead galaxy has absorption, dark lines cut down. These are the fingerprints of the cool stars themselves, the light of the whole galaxy filtered through the outer atmospheres of its aging suns, each element in those atmospheres swallowing its own particular colour. The hydrogen leaves a whole ladder of dark bands, the Balmer series, running through the spectrum like the rungs of a fading staircase. The calcium leaves its two deep scars, and crucially the emission lines that mark star formation, the oxygen, the hydrogen glow of hot gas, are simply absent. That absence is not nothing. That absence is the loudest thing in the spectrum once you learn to hear it. The absence of those emission lines is the direct statement that no hot gas is being lit up, that no massive young stars are pouring out the radiation that would make gas glow, that star formation has stopped. In a living galaxy, those lines scream. In GS 9209 they are silent, and the silence is the diagnosis. You're looking at a galaxy that has stopped making stars, and you know it not from any single number, but from the whole shape of the light, the missing spikes and the deep cliff and the dark rungs of the hydrogen ladder, all of them together spelling out the same word, quenched, in a language of colour that took us a century to learn to read. The absorption lines in GS 9209's spectrum were among the deepest ever measured anywhere in the universe. One of the dark hydrogen lines, called H delta, was so strong, carved so deeply into the light, that its measured width placed it at the very extreme edge of what has ever been recorded, at nearly 8 angstroms of what astronomers call equivalent width, a way of measuring how much light the line has swallowed. That depth is a clock. The deeper those lines, the more thoroughly the galaxy is dominated by the aftermath of a starburst rather than by ongoing starbirth. GS 9209 was not a galaxy dimming slowly. It was a galaxy that had slammed its furnace shut hard and fast, leaving behind a population of stars all aging together, all sliding down the same slope into the red, all born in the same brief season, and now growing old in unison, like a single generation with no children coming after them. And here is the thing that should make you sit up, or rather, since you're meant to be lying down, the thing that should settle into you like a stone dropped into still water. This galaxy, GS 9209, contained roughly as many stars as the Milky Way. Nearly 40 billion suns, give or take, packed into a single galaxy. And it had built all of them, and then shut down, all before the universe was even 1 billion years old. The light we caught from it left when the cosmos was around 1.25 billion years old, a mere infant. And by then GS 9209 was already an old galaxy, already dead, already coasting on the light of stars that had formed and aged and begun to fade while the universe was still learning how to make galaxies at all. At its peak, before it died, it had been building stars at a rate of around 490 new suns every single year. Try to hold that number for a moment. Nearly 500 stars a year, each one the equal of our own sun or larger, igniting one after another year after year for a couple of 100 million years, until it had assembled 38 billion of them, and then, all at once, it stopped. But the number of stars is only half the strangeness. The other half is where they were kept, because GS 9209 held its nearly 40 billion suns in a space almost impossibly small. The Milky Way is a vast, sprawling pinwheel, a disk of stars 100,000 light-years across, so wide that light itself, the fastest thing there is, takes 100,000 years just to cross it. GS 9209 was nothing like that. Its stars were packed into a region whose effective radius was around 220 parsecs, which is about 717 light-years. Compare that to the Milky Way's radius, tens of thousands of light-years, and you find that GS 9209 was roughly 60 times more compact, 60 times smaller in radius, and yet holding a comparable weight of stars. Try to feel what that means. Imagine taking every star in the Milky Way, all of the ones you can see on the darkest night and all of the billions you cannot, and imagine compressing them, gently and impossibly, into a volume so small that the whole thing would fit inside one of the little satellite galaxies that orbit our own. The stars would be crowded together at a density that has no equal in the sky near us. If you lived on a planet inside GS 9209, the night sky would not be a scattering of faint points. It would be a blaze, thousands upon thousands of stars bright enough to read by, the whole vault of the heavens crowded with light. The nearest neighbours so close that they would burn like distant street lamps in the fog. There would be no true night. There would be no darkness in which to see the deep universe beyond, because the local stars would drown it all out, and every single one of those stars would be old. Every one of them would already have formed and aged and begun to cool before the raw material of our own sun had even begun to gather itself together in some distant, quieter corner of the growing universe. There is a kind of vertigo in that. Not a fear exactly, but a loosening. The sensation of a floor you thought was solid turning out to be a surface floating on something much deeper. We're used to thinking of ourselves as latecomers to a universe that took its time. We imagine a slow, patient build-up, small things becoming larger things over unimaginable ages, and somewhere near the end of that long assembly, us. And then the light of GS 9209 arrives and quietly informs you that a galaxy the size of your own home galaxy had already finished its entire life story, birth to death, before the story of your galaxy had even properly begun. That is not how it was supposed to go. That is not the shape the universe was supposed to have, and yet the light does not lie. The light is just light, arriving after its long cold journey, carrying its little cliff at 4,000 angstroms, and its deep, dark hydrogen lines, and its silence where the bright lines of life should be. It does not care what we expected. It only reports what happened. GS 9209 is not alone, and that is the part that turns a curiosity into a crisis. If it were the only one, you could shrug. You could call it a fluke, a lottery ticket. The one galaxy in a billion that happened to sprint through its life ahead of schedule. Nature is large, and large numbers throw up strange things, but GS 9209 is not the only one. It is not even the strangest. It is simply one of the first that we managed to read clearly, and once we knew how to read them, we began to find them everywhere we looked, in every direction, in every deep field, hiding in plain sight. There is a galaxy called ZF-UDS 7329, and its story bends the mind in a slightly different direction. We catch its light at a moment when the universe was about 2 billion years old. That already makes it ancient. But when astronomers measured the ages of the stars inside it, weighting the measurement by how much mass each population of stars carried, they arrived at a figure that seems, at first, like it must be a mistake. The stars, on average, appeared to be around 2.33 billion years old. Older than the universe was at the moment we see them. Sit with that for a moment, and then let me be honest with you, because this story deserves honesty as much as it deserves wonder. That comparison, a stellar age older than the universe, is not quite the paradox it sounds like. It is a comparison between a measured average age, which carries real uncertainty, and the age of the cosmos at that instant, and the error bars on such measurements are wide. It is a vivid way of saying something true rather than a literal impossibility. The stars are not really older than time. But what the measurement points to is genuinely staggering. It means that the stars of ZF-UDS 7329 formed extraordinarily early. It means that this galaxy, holding something like 100 billion suns worth of stars, built the bulk of that mass in the first 400 million years of cosmic history, at an epoch we describe with a redshift number of around 11, when the universe was barely emerging from its dark ages, when the first light was still learning how to fill the void, when there had barely been time for anything to form at all, and you can see that early formation written right into its spectrum, the same way you could read it in GS 9209, only pushed even further toward the ancient. When astronomers took ZF-UDS 7329's light and spread it out, they found the same telltale signs of death: the deep Balmer break, the smooth red continuum, the dark absorption lines of cool old stars, and the flat silence where the emission lines of star formation should have been. But they found something more, a chemical fingerprint that spoke to how the galaxy formed. The relative amounts of different elements in its stars told a specific story. There was an enhancement of what astronomers call the alpha elements, things like magnesium compared to iron. This ratio is a clock of a different kind. Magnesium and its cousins are forged mostly in the swift deaths of the most massive stars, the ones that explode within a few million years of forming. Iron is built up more slowly, over hundreds of millions of years, released by a different and more patient kind of stellar explosion. When a galaxy is rich in magnesium relative to iron, it is telling you that it made all its stars in a hurry, in a single fast burst, and shut down before the slow iron makers had time to enrich the gas. It is the chemical signature of a galaxy that lived fast and died young, a whole population formed in one brief violent season and then left to age. ZF-UDS 7329 carried that signature clearly. Its stars were not only old, they were the product of a single, rapid, ancient burst, and the ratio of its elements, measured across 12 billion years of distance, confirmed a formation so early and so fast that it pressed against the edge of what the young universe could possibly have supplied. And that is where the trouble truly begins, because there is a rule, a deep rule, about how much a galaxy is allowed to weigh at a given moment in time. When the universe was young, its matter had not yet gathered into the great scaffolding of galaxies we see today. According to the theory we trust, the ordinary matter that makes stars, the hydrogen and helium, is always outnumbered by a mysterious invisible substance called dark matter, and the ratio between them is fixed, set in the first instance of the Big Bang. A galaxy can only make stars out of the ordinary matter that falls into its gravitational well, and the size of that well is set by how much dark matter has managed to clump together around it. This gives you a hard ceiling. There is only so much ordinary matter to go around. There is only so much gas a young galaxy can possibly have. The Big Bang set aside only a certain allowance of hydrogen and helium for each little well of gravity, and no galaxy is supposed to be able to spend more than its allowance. ZF-UDS 7329 appears to have spent more than all of it. To build the stars it has, this early and this fast, it would have needed to convert ordinary matter into stars at an efficiency higher than the total supply of ordinary matter available to it. The literature states the problem in blunt terms. Its stellar mass and age would have required a fraction of ordinary matter to dark matter higher than the cosmic value, which is, in plain language, impossible under the standard picture. It is as if you found a house built of more bricks than could possibly have been delivered to the site. Something in the accounting does not balance. The bricks are there, the house is there, tall and finished and lived in, and the delivery records say the bricks could not have arrived. Someone, somewhere, has built, with materials that the ledger says never existed. This is the shape of the problem we're going to sit inside tonight. Not a single strange galaxy, but a pattern of them, each one pressing on the edges of what our theories allow, each one a little too big, or a little too dead, or a little too old, or a little too soon. And the more of them we find, the harder it becomes to explain them away as mistakes or flukes or freaks. They're starting to look like a feature of the early universe, not a bug. They're starting to look like something the universe was doing all along, quietly, in the deep dark of its first billion years, while every simulation we built to predict its behavior insisted it could not be happening. The universe was breaking our rules, and it was doing so at scale, and it left the evidence lying around in the deep sky for anyone patient enough and equipped enough to find. Tonight we're going to sit with that imbalance rather than solve it, because it is the kind of quiet impossibility that a mind can rest against as it slides towards sleep. But before we get lost in what these galaxies break, it is worth slowing down and returning to the beginning of the human side of this story, because it is a story of patience, and patience is a good thing to think about as you drift towards sleep. These galaxies did not announce themselves. They did not arrive with fanfare. They sat in our data for the better part of 20 years, faint and red and unreadable, teasing the astronomers who found them with a signal none of the instruments of the time could decode. GS 9209 was first noticed in the year 2004, not by James Webb, which would not fly for another 18 years, but by the Hubble Space Telescope, that faithful old workhorse that gave us so many of our first clear looks at the deep sky. A researcher named Karina Caputi picked it out of Hubble's images as one of a scattering of faint red objects that looked, from their colours alone, as though they might be old. Photometrically, as astronomers say, meaning judged by the broad colours of their light rather than by a proper spectrum, these objects had the look of massive, aged, quiescent galaxies. But looking like something is not knowing it. To know, you need a spectrum. You need to spread the light into its colours and read the lines, and GS 9209 was too faint and too red for any telescope on the ground to do that. Picture the frustration of it. For nearly 20 years this galaxy sat in the catalogue, a faint red smudge with a name and a position, and a set of colours that whispered old, old, old. Astronomers pointed the great ground-based telescopes at it, the ones on the mountaintops of Chile and Hawaii, the giants with mirrors wider than a house, and the spectrographs came back with noise. The light was too dim, stretched too far into the infrared by the expansion of the universe, buried too deeply in the glow of Earth's own warm atmosphere. The universe was teasing us with a signal we could not read. The message was there, written in ancient light, sitting in the catalogue with a name and a set of coordinates, and we did not yet have the ears to hear it. It was like holding a letter written in an ink that only becomes visible under a light we did not possess, turning the page over and over in our hands, knowing it said something, unable to read a word. This was not GS 9209's problem alone. It was the shape of the whole field. Astronomers had assembled catalogues full of these faint red candidates, dozens of them, objects that might be massive dead galaxies from the early universe, or might be something else entirely. Dusty galaxies still furiously making stars behind a curtain of obscuring grime, their blue light reddened not by age but by dust. From the colours alone, you could not always tell the two apart, and that ambiguity was maddening. An old dead galaxy and a dusty living one can wear the same red coat. Only a spectrum can tell you what is underneath. In one careful study, 10 of 12 promising candidates could not be confirmed by any ground-based telescope in existence. They hung there in the data, unverified, ghosts in the photometric catalogues, real enough to publish as candidates but never solid enough to call proven, a list of maybes stretching back years. One astronomer described the situation with a particular galaxy in words that capture the whole era. It was too red, and it was too faint, and we could not measure it. That was the wall. That was the limit. Everything about these galaxies conspired to hide them from us. Their light was old, which made it faint. Their most important features, the Balmer break and the dark absorption lines, sat at wavelengths that the expansion of the universe had stretched far into the near-infrared, into a part of the spectrum where the sky itself glows, and where the older instruments simply could not see clearly. To read these galaxies you needed a telescope in space, above the glow of the atmosphere, cooled to a temperature near absolute zero, so that its own warmth would not blind it, carrying an instrument designed from the ground up to catch and split the faint infrared light of the most distant objects in creation. You needed James Webb, and so for nearly 2 decades, these galaxies waited. They had been dead for more than 12 billion years already, A little more waiting was nothing to them. They sat in the catalogues, patient as only dead things can be, while a telescope the size of a tennis court was designed and argued over and delayed and built and delayed again and folded up like a piece of impossible origami and launched on a pillar of fire on a cold morning at the very end of the year 2021 and sent to a point in space 1,000,000 miles from the Earth, where it slowly unfurled its golden mirror, petal by petal, and cooled itself in the shadow of a sunshield the size of a tennis court, until at last it opened its eye on the deep sky and began to gather the oldest light in the world. Every step of that journey could have failed. Hundreds of things had to unfold perfectly, in sequence, in the dark, with no hope of repair. And they did. And the telescope cooled and steadied and looked. When Webb's spectrograph, an instrument called a NIRSpec, the near-infrared spectrograph, finally turned toward GS9209 and held its gaze for 5 hours on that November night in 2022, it caught photons that had been travelling through the dark for something like 12.5 billion years. These were not ordinary photons. Each one had left GS9209 when the universe was an infant, had crossed the widening gulf of expanding space for longer than the Earth has existed, had slipped past countless other galaxies, and through the thin, cold medium between them, unabsorbed, unscattered, patient, and had arrived, at last, at a golden mirror floating in the shadow beyond the moon. The spectrograph took that ancient light and spread it into its colours, and there, written in the pattern of the light, was the answer to a 20-year-old question. The Balmer break, sharp as a cliff, the dark hydrogen lines deep as any ever seen, the silence where the bright lines of life should have been. GS9209 was dead, and it had died young, and now, finally, we could prove it. You could pause here, and it would be a good place to pause. But I want you to hold on to one small human detail, because it grounds all of this in something you can feel. Somewhere on Earth, in an office in Edinburgh, an astronomer named Adam Carnell opened the data from those 5 hours and looked at the spectrum of a galaxy that had died before the sun was born, and understood in a single quiet moment what it was showing him. There was no fanfare in that moment. There rarely is. Just a person, and a screen, and a thread of impossibly old light, and the slow dawning realization that the universe had been doing something in its infancy that no one had believed it could do. That is how these things actually happen, not with a bang. With a quiet person in a quiet room, reading the mail from the beginning of time, and feeling the small cold thrill of understanding something that no human being had ever understood before. Before we go on, let me say one thing, gently, only once, and then we'll return to the galaxies and I won't interrupt again. If you're finding that this slow way of telling the story helps quiet your mind, if these long unhurried nights are becoming part of how you fall asleep, then it would mean a great deal if you followed along wherever you're listening, and if you're on Spotify, following there helps these quiet documentaries find the next person lying awake in the dark who needs a long, calm voice to drift off to. That's all. No more of that tonight. Let's go back to the dead. Tonight we're going to walk together through that whole hidden population, one strange galaxy at a time, so let the names wash over you without any effort to hold them. Once Webb had proven that GS9209 was real, that a massive dead galaxy could exist that early, the floodgates opened, though quietly, the way floodgates open in a story where everything happens across billions of years. Because it turned out that GS9209 was not the earliest. It was not the strangest. It was simply the first door, and behind it stood a whole hall of them, each opening onto a galaxy stranger than the last, each one confirming that we had not stumbled onto a single freak, but onto an entire hidden population. There is a survey with a bright, cheerful name, Rubies, which is the sort of acronym astronomers assemble when they want their program to be memorable. The people who ran it had a simple and ruthless strategy. They looked through the images Webb had already taken of the deep sky, and they picked out the objects that were reddest and brightest and most extreme. The edge cases, the ones most likely to be something strange, and they fired the spectrograph at them one after another. It was a kind of triage for the cosmos, a hunt for the places where the universe behaved most unlike the way it was supposed to. They were not looking for the ordinary, they were looking for the impossible, the outliers, the things that would either turn out to be mistakes or turn out to be revelations, and rubies kept coming back with dead galaxies from times and places where dead galaxies were not supposed to be. One of them is called Ruby's Eggs QG1, and its light comes to us from a moment when the universe was around 1.2 billion years old. This galaxy holds roughly 100 billion suns worth of stars, about the same as the whole Milky Way, and it built them in a single burst that lasted only about 180 million years. During that burst, at its peak, it was forming stars at a rate of around 870 new suns every single year. And then, over a span of only about 100 million years, it shut down. It went from a raging engine of star formation to a dead, silent, cooling husk in a window of time shorter than the gap between one mass extinction on Earth and the next. It burned like a bonfire soaked in oil, and then someone closed a lid over the whole thing and it went out. And here is the detail that turns Ruby's Eggs QG1 from a curiosity into a genuine problem, a detail so important that it deserves to be said slowly. When astronomers looked at this galaxy, they measured how much its red colour came from age and how much came from dust. Because that is the great escape hatch, the loophole that could make all of this go away. If these red galaxies were not really dead, if they were secretly still making stars behind a thick curtain of dust that reddened their light and hid their youth, then there would be no mystery at all. Dusty star-forming galaxies are common. They are not strange. They do not break any rules. A red colour on its own does not prove death. It could just be a living galaxy seen through a veil. So they measured the dust. And in Ruby's Eggs QG1, the amount of dust dimming the light was extraordinarily low, so low that it could account for almost none of the redness. The red colour was not the red of dust. It was the red of age. There was no curtain. There was no hidden furnace still burning behind a veil of grime. The galaxy was exactly what it appeared to be, an old dead quiescent thing, its stars all formed long ago and now cooling together in the dark. The loophole was closed. The escape hatch was sealed. This galaxy was really truly dead, and it had died really truly early, and no amount of hoping it was secretly a dusty starburst could make that fact go away. When the astronomers reached for the comfortable explanation, the one that would let the universe stay ordinary, it slipped through their fingers. Then there is a galaxy called Ruby's UDS QG7, which does not roll off the tongue, but which holds, at least for now, a very particular record. Its light left it when the universe was only around 700 million years old. 700 million. In the whole span of cosmic history, which runs to nearly 14 billion years, this is the first small fraction, the opening chapter, the part of the story where the ink is barely dry, and already, at that impossibly early moment, this galaxy was dead. It held more than 10 billion suns worth of stars, some estimates put it far higher, packed into a region only about 650 light-years across, one of the most physically compact, massive galaxies ever seen. Its spectrum showed one of the strongest Balmer breaks anyone has ever observed at that epoch. The telltale cliff, the mark of a stellar population that had already grown old. It showed iron and magnesium in absorption, the metals cooked up inside earlier generations of stars and then scattered through the galaxy when those stars died. A sign of chemical maturity that takes time, that takes generations of stars living and dying and seeding the gas with their ashes. And yet here it all was, in a galaxy we catch in the universe's first 700 million years. A galaxy that had somehow already run through several generations of stars in an epoch when most of the universe was still assembling its very first ones. This galaxy is the most distant confirmed dead galaxy we have ever found, and the gap between it and the previous record is not small. It sits more than 2 full redshift units beyond anything confirmed before Webb, which is a technical way of saying it pushes the boundary of known cosmic death back by hundreds of millions of years, into an epoch that everyone had assumed was far too young, far too raw, far too busy building its first galaxies to have any of them finishing and dying already. The astronomer who led the work, Andrea Weibel, put the implication plainly. Galaxies like this one, this early, appear to be more than 100 times more abundant than any model to date had predicted. Not a little more common than expected. More than 100 times more common. The models, in other words, were not slightly wrong. They were wrong by a factor that turns a rare freak into a whole hidden population. Wrong in a way that cannot be patched with a small adjustment. Wrong the way a map is wrong when it shows an ocean where there is a continent. And then, gentlest of all, there is a galaxy that breaks a different assumption entirely, and it does so precisely because it is small. It is called JADES GS Z7.01QU, and it comes to us from the same impossibly early epoch, only about 700 million years after the Big Bang. But unlike the giants, this one is a dwarf. It holds only a few hundred million suns worth of stars, a fraction of a percent of a galaxy like the Milky Way. A small thing by any measure. It formed its stars in a brief flurry lasting somewhere between 20 and 100 million years, and then it too went quiet. When astronomers spread out its light, they found the Balmer break, and they found no glowing hydrogen, and no ionized oxygen, and no signature of hot gas anywhere. The lines where life should have been were flat. The galaxy that should have been screaming with the light of star formation was instead completely silent, hushed, holding its breath in the dark. And that silence in a galaxy this small is a puzzle all its own. Because the leading explanation for how big galaxies die, the one we're going to spend a good long while inside tonight, involves the enormous black holes at their centres, engines of a scale that only the largest galaxies possess. A dwarf galaxy is not supposed to have that kind of engine. It is not supposed to be able to shut itself off. And yet here is one that did, sitting in the transition zone where star formation is supposed to sputter and flicker but not stop. A galaxy that went dark when the rules said it should still be flickering back to life. Its story is not finished, and it may not even be truly over. Some astronomers suspect this small galaxy might only be pausing, holding its breath, and might yet gasp back to life and resume making stars in the deep future we cannot observe. Because at these small masses and early times, star formation is supposed to come in fits and starts, bursts and lulls, rather than steady burning. But at the moment we catch it, it is dead, or as close to dead as makes no difference, and it is far too small to have died the way the big ones are supposed to. It is a quiet little contradiction, floating in the first light of the universe, a small dark question mark that no one has yet erased. It is worth pausing, before we count them all, on how these galaxies actually appear in the images themselves, because the eye expects something grander than what is really there. When you finally pull up the picture of one of these ancient dead galaxies, having read about its 40 billion suns and its monstrous black hole and its impossible early death, you might expect something majestic, something worthy of the story. What you get is a smudge, a faint reddish blob, a few pixels across, barely brighter than the noise of the deep sky around it, so unremarkable that if you did not know its coordinates you would pass right over it. There are no spiral arms. There are no glittering knots of blue star-forming regions. There is no structure at all that the eye can grab hold of. Just a small, dim, red patch, floating in the black, easy to mistake for a flaw in the detector or a speck of dust on the lens. And that is the strange humility of these objects. They contain the mass of a galaxy, the drama of a rapid birth and a violent death, an engine of pure darkness at the centre still faintly turning, and from our distance, across all those billions of light years, all of that grandeur collapses into a faint red smear that would fit on the head of a pin held out at arm's length against the night. In the press, some of these compact red objects have been called little red dots, a plain name for a plain-looking thing, though the formal population that name refers to is a related and separate puzzle of its own, another kind of red mystery that Webb has stirred up and not yet resolved. The point is that the greatest strangeness in the sky rarely looks strange at all. It looks like almost nothing. You have to read the light to know what you're holding, so this is the shape of the graveyard then. Giants like GS9209 and Ruby's EGS-QG1 holding the mass of whole modern galaxies in tiny compact volumes, dead within the first billion years. Record breakers like Ruby's UDS-QG Z-Sven, already old and chemically mature when the universe was 700 million years young. Relics like ZF-UDS-7329, whose stars are so old they brush against the age of the cosmos itself, and small, strange things like the little quenched dwarf, dead when it had no business being able to die. Not one galaxy, a population, a whole cemetery, spread across the deepest fields of the sky, hidden for 20 years, and now finally readable. A graveyard we had been photographing for decades without ever realizing what the faint red smudges in our images actually were. Tonight we're going to take a census of that graveyard, and the number will surprise you. And the deeper we look, the more of them we find. Which brings us to the part of the story where the mystery stops being about individual galaxies and starts being about numbers, about how many, about a census of the dead. When two of the deepest surveys Webb has conducted were combined and searched carefully for these massive dead galaxies, they turned up 225 candidates in a single patch of sky. 225. And that patch of sky was small. It covered an area roughly the size of 2 full moons placed side by side against the vault of the heavens. 2 full moons worth of sky, and inside it, more than 200 dead galaxies from the early universe, every one of them having lived and burned and died more than 10 billion years ago. Every one of them invisible to us for the entire history of astronomy, until a telescope with a golden mirror unfolded itself beyond the moon, and finally caught their faint red light. And when astronomers sort those candidates by cosmic epoch, the census tells an even sharper story, one worth walking through slowly. The great majority of them sit at the nearer end when the universe was between about 2 and 3 billion years old, where dead galaxies are common and expected and nobody is surprised to find them. There, the count runs to well over 100, more than 150 in that nearer bin alone. But as you push earlier, into the harder, younger epochs, the numbers thin, and yet they never vanish. When the universe was younger still, roughly 1.5 to 2 billion years old, there are dozens more, some 60 of them. And when you reach all the way back to when the universe was only around 1.25 billion years old, deep into the territory where the simulations predict almost nothing, there are still more than a dozen robust candidates, genuine massive dead galaxies caught in an epoch where the models say the graveyard should be all but empty. That is the number that matters. Not the total, but the way the total refuses to fall to zero as you push back in time. The graveyard is not empty at the early end. It is thinly populated but unmistakably occupied, and every occupant is a galaxy the models cannot make. There is another way to say this that cuts even closer to the bone. Astronomers talk about the quenched fraction, the fraction of the most massive galaxies at a given epoch that have already died. In the nearby universe, this fraction is high. Most big galaxies today are dead, red and gas-poor and finished. The expectation from every pre-Webb model was that this fraction should plummet towards zero as you go back in time, that in the early universe essentially all massive galaxies should still be alive and forming stars, because there had not yet been time for any of them to die. Instead, Webb finds that the quenched fraction stays stubbornly, measurably above zero all the way back into the first billion years. It is not the majority, not out there in the deep past, but it is not nothing either, not a rounding error, not a handful of freaks. It is a real and persistent fraction of the most massive galaxies already dead at epochs where the models predicted a living universe. The graveyard, in other words, was open for business almost from the beginning, taking in its first residents while the universe was still in its infancy, and it never once stood empty. This is the fact that should settle the matter of whether these galaxies are flukes. They are not flukes. Flukes do not come 200 at a time in a scrap of sky the size of 2 moons. This is a population. This is a feature of the young universe, a thing it was doing all over, quietly, in every direction we now know to look. Point Webb at any sufficiently deep patch of sky, hold the exposure long enough and you will find them. The dead galaxies of the first billion years are everywhere. They always were. We simply could not see them, and the not seeing lasted the entire history of our species right up until a few years ago. Every human who ever looked up at the night sky, every astronomer who ever charted the heavens, every stargazer in every culture across all of recorded time, missed them completely. They were there the whole while, their light falling steadily on the earth, and we had no way to know. Tonight we're going to hold that thought gently and turn to the rulebook these galaxies keep breaking. Now, to understand why this is such a problem, why it keeps astronomers up at night in a way that most surprising discoveries do not, we have to talk about the rulebook. We have to talk about the theory that these galaxies are quietly breaking. And I promise to do this gently because the theory has a long and honest name and a great many moving parts. But the heart of it is simple enough to hold in a drowsy mind. The theory is called lambda cold dark matter, which astronomers shorten to lambda CDM, and it is one of the great triumphs of modern science. It describes how the whole universe grew from the smooth, hot, nearly featureless state it was in just after the Big Bang, into the vast cosmic web of galaxies and clusters and filaments and voids we see today. It gets an astonishing number of things right. It predicts the faint temperature ripples in the afterglow of the Big Bang, the cosmic microwave background, to a precision of several decimal places. It explains why the universe looks like a great sponge of luminous filaments wrapped around enormous empty voids. It describes the expansion of space across nearly 14 billion years. It is not a fragile theory. It is one of the most tested and most successful ideas in the history of physics, and nothing about the dead galaxies is going to overturn it wholesale. But it makes one prediction about how galaxies grow, and it is that prediction, and that prediction alone, that the dead galaxies seem to be breaking. The prediction is this: galaxies are supposed to grow from the bottom up. They are supposed to be built hierarchically, small things merging into larger things over enormous spans of time. In the beginning, the theory says, the dark matter, that invisible stuff that outweighs ordinary matter by a factor of 5 or so, gathered into small clumps first, little wells of gravity. And ordinary gas fell into those little wells and made small galaxies, and then those small galaxies drifting through space occasionally collided and merged, building up larger galaxies, and those larger galaxies merged into larger ones still. It is a slow process. It is a patient process. It takes billions of years. Think of a great city that grows not all at once, but from villages, villages becoming towns, towns slowly knitting together into a metropolis over centuries, each stage building on the last, each generation adding a little more than the one before. That is how galaxies were supposed to form. Small first, then large, and always slowly, always in that order, never skipping a step. It is worth walking a little more slowly through what this bottom-up picture actually meant, because the sharpness of the surprise depends entirely on how firmly the old expectation was held. In the standard story, the first things to form after the Big Bang were not galaxies at all, but tiny overdense regions, places where the density of matter was a hair above the average, so slight a difference that you would never notice it by eye. Gravity is patient, though, and gravity does not forgive an imbalance. Wherever there was a little more matter, gravity pulled in a little more still, and those regions grew denser while the emptier regions grew emptier. Over millions and then hundreds of millions of years, the rich growing richer and the poor growing poorer, until the densest knots collapsed into the first small halos of dark matter. And these first halos were small. That was the whole point. The theory said that structure grows from the smallest scales upward, that the little things must come first and the big things must wait, assembled later out of the accumulated debris of countless small collisions. A galaxy the size of the Milky Way in this picture is not a thing that forms. It is a thing that is built, slowly, across most of the age of the universe, out of dozens or hundreds of smaller galaxies that fell together one at a time over billions of patient years, and this had a specific and testable consequence, one that everyone in the field understood. The most massive galaxies should be the last to finish. They require the most mergers, the most accumulation, the most time. A galaxy holding 100 billion suns should not appear early, because early on there has simply not been enough time for all those smaller pieces to find each other and fall together. The biggest galaxies should be the latecomers, still assembling, still growing, still messy and unfinished, even at what astronomers call cosmic noon, the era a few billion years in when star formation across the whole universe reached its peak, when the sky was busiest with the making of stars. If you had asked an astronomer in the year 2000 when the giant galaxies finished forming their stars, the honest answer, drawn straight from the theory, would have been late, relatively late. Certainly not in the first billion years, almost certainly not before the universe had even properly warmed up. The giants were supposed to be still under construction long after the moment where Webb now finds them already finished and cold. But there was already a crack in that expectation, a warning sign that appeared in the data years before Webb, and it is worth knowing about because it means the shock we are describing did not come entirely without notice. Astronomers noticed in the early 2000s something they called downsizing, and the name captures the strangeness of it. When they looked at galaxies across cosmic time, they found that the most massive galaxies seemed to have formed their stars earliest and fastest, and then shut down first, while the smaller galaxies kept forming stars for much longer, trickling along into the recent universe. This was exactly backward from the naive hierarchical expectation. The big galaxies, which were supposed to be the slow latecomers, were instead the early finishers. The small galaxies, which should have formed quickly and settled down, were the ones still puttering along making stars billions of years later. It was as if the largest structures had rushed through their whole lives first and the smallest had dawdled. Downsizing was a real, measured, repeatable pattern, seen again and again in survey after survey, and it sat awkwardly against the theory for the better part of 2 decades. Astronomers found ways to fold it into the models, to explain it with clever tuning of how feedback works in galaxies of different sizes, and for the most part the patch held well enough. But downsizing was, in hindsight, the early universe clearing its throat, a first quiet hint that the biggest galaxies did their living early and their dying early, a hint that the neat bottom-up timeline had a wrinkle in it that no one had quite managed to iron out. When Webb finally looked into the first billion years, it did not so much overturn a settled expectation as confirm, in the most extreme possible way, a suspicion that had been nagging at the edges of the field for 20 years. The wrinkle was not a wrinkle, it was a tear, and it ran deeper than anyone had let themselves believe. The dead galaxies of the early universe shatter this picture. They are not small, they are enormous, holding the mass of whole modern galaxies. They are not slow. They assembled their vast populations of stars in bursts lasting a couple of 100 million years, a geological eye blink, and they are not late. They finished and died in the universe's first billion years, at the very dawn of cosmic time, when the hierarchical picture says there should have been only small galaxies, only villages, only the earlier stages of a process that takes eons to run its course. Finding a massive, fully formed, already dead galaxy at that epoch is like finding a photograph of a city in its 5th year of existence and seeing, standing in the middle of it, a skyscraper that should have taken 80 years to build. The construction timeline does not fit. The building is there, tall and finished and already going dark, its windows unlit, and the calendar says it could not possibly be, and yet there it stands. This is where the simulations come in, and where the trouble becomes precise instead of merely vivid. Because we do not just have the theory in the abstract, we have built enormous computer models that take the theory and let it run, that fill a virtual universe with virtual dark matter and virtual gas, that let gravity pull it all together over billions of simulated years, and that grow virtual galaxies according to the best physics we know. These simulations have names like IllustrisTNG and Astrid and Eagle, and they are triumphs of human effort, running for months on supercomputers, tracking tens of millions of particles of gas and stars and dark matter and the black holes that grow at galactic centres. They are our best attempt to build a universe inside a machine and watch it evolve, and in most respects they succeed beautifully. The virtual universes they produce look remarkably like the real one, full of spirals and ellipticals and clusters and cosmic web. You can fly through them and mistake them for the real thing, except in one place. When you take one of these simulated universes and you search it for massive dead galaxies in the first billion years, the kind Webb keeps finding in the real sky, you find almost none. In some of the simulations at the earliest epochs, you find exactly 0. The virtual universe simply does not make them. It cannot make them fast enough. Its galaxies are still busy being villages and towns, while the real universe was already producing finished darkened cities. And when you count carefully and compare the numbers, the gap is not small. The simulations underpredict the number of these early dead galaxies by a factor that runs from 10 to as much as 100. 2 orders of magnitude in the worst cases. The real universe made these things 100 times more often than our best model of the universe says it should have. The simulated cosmos and the real cosmos, laid side by side, look in this one respect like 2 different places, as if the machine and the sky were telling 2 different stories about the same childhood. Let me give you the single sharpest version of this, because it is the kind of fact that lodges in the mind. Take Ruby's Eggs QG1, the galaxy with 100 billion suns that died in the universe's first billion years, the one whose red colour came from age and not dust. When astronomers looked into the IllustrisTNG simulation, that vast and careful model of cosmic evolution, and asked how many galaxies like Ruby's Eggs QG1 it produced across its entire simulated volume, the answer was 1, exactly 1, in the whole simulated cosmos at that epoch, and yet in the real sky, galaxies like it appear something like 130 times more often than that. The simulation, encoding decades of physics, running for months on a supercomputer, predicted a single needle in an enormous haystack. Webb pulled out 130 needles, and it was barely trying. The astronomers who made the comparison noted with a kind of dry astonishment that even at those revised elevated numbers, Ruby's Eggs QG1 was still an outlier, still stranger than the strange, still a thing that pushed against the edge of what even a corrected model could comfortably hold. To understand why the simulations fail so badly here, and why the failure is instructive rather than embarrassing, you have to understand a little about how these models are actually built, and in particular about the word subgrid. A cosmological simulation divides the universe into a vast grid of tiny cells, or represents it with vast numbers of particles, and it computes, cell by cell and step by step, how gravity pulls the matter around. Gravity is easy in the sense that we understand it exactly, but the things that actually make a galaxy live and die, the way gas cools and condenses, the way stars ignite, the way a black hole feeds and blows out its winds, all of that happens on scales far smaller than any cell in the simulation. a single cell might be larger than a whole star-forming region. The simulation cannot resolve what happens inside it, so the modelers do something necessary and slightly uncomfortable. They write rules, by hand, that say what a cell should do based on its conditions. If a cell is dense and cool enough, turn some of its gas into stars at such and such a rate. If a black hole is present, let it feed at such and such a rate and blow out such and such a wind. These handwritten rules are the subgrid physics, and they are not derived from first principles. They are prescriptions, informed guesses, tuned to make the simulation match the real universe. And here is the crucial point. They were tuned to match the universe we could already see, which before Webb meant the universe at cosmic noon and later, the nearby well-studied cosmos. The AGN feedback rules in IllustrisTNG and Eagle and the others were dialed in until the simulated galaxies at those later epochs had the right masses, the right colours, the right proportions of living and dead. The models were calibrated against a universe a few billion years old and older, because that was the only universe we had good data for. Nobody tuned them against the first 700 million years, because nobody could see the first 700 million years clearly enough to tune against. So when you take those carefully calibrated models and run them back to the very early universe and ask what they predict there, you're asking them to extrapolate far outside the range where they were ever tested. And they predict, at redshifts beyond 4, number densities of massive dead galaxies that are vanishingly small, in some cases so small that across the entire simulated volume there is essentially nothing to find. The models were honest about the universe they were built to describe. They were simply never built to describe this one, the wild early one, and when pushed into it they broke, not because the dark matter was wrong, but because the little handwritten rules for how black holes behave were calibrated on a tamer, later cosmos, and could not imagine the ferocity of the young one. Which brings us to the response, and to a word that is doing an enormous amount of work in the current debate, the word super-Eddington. But we will come to that in its proper place, once we have felt the full weight of the problem. For now, hold on to this. The simulations do not fail because the theory of gravity is wrong, or because dark matter is a fiction. They fail because the rules we wrote by hand for how black holes eat and how galaxies die were guesses fitted to a universe we could see and the universe we could not see, until now, played by fiercer rules than our guesses allowed. There is a phrase astronomers use for the wider version of this trouble, and it is a good one, honest and a little rueful. They call it the impossibly early galaxy problem, because the dead galaxies are not the only thing Webb has found that arrived too soon. It has found galaxies still furiously making stars that are far brighter and more massive than they should be at the very earliest times we can observe. It has found large, orderly disk galaxies, smooth rotating pinwheels, at epochs when there should only have been chaotic clumps. It has found galaxies with mature central bulges when there should only have been formless assembly. Everywhere Webb looks in the early universe, it seems to find things that are too big, too orderly, too finished, too soon. And the dead galaxies are the most extreme version of this pattern because they are not just too big and too soon, they are too big too soon and already over. Not only did they build themselves faster than the rules allow, they also finished and died faster than the rules allow. They are the impossibly early galaxy problem taken to its logical conclusion and then buried, the final chapter of a story that was not supposed to have even reached its middle yet. So the question that hangs over all of this, the question you can carry with you towards sleep, is a question about death. Not just how these galaxies got so big so fast, though. That is strange enough. The deeper question is how they stopped. How does a galaxy that is forming 500, 800, nearly 1,000 new suns every year, a galaxy blazing with the light of ongoing creation, an engine at the full roar of its power, how does a thing like that switch off? And not just switch off, but switch off fast in 100 million years or less, and then stay off, refusing to reignite even though it is surrounded by the raw material of a young gas-rich universe. What kills a galaxy? And what kills it that quickly, that completely, that early? What could possibly reach into the heart of a furnace roaring with the making of 1,000 suns a year, and in the space of a geological instant, put it out and keep it out? Tonight we're going to name the leading suspect, and it is the darkest object in creation, and it sits at the very heart of the galaxy it destroys. At the centre of nearly every large galaxy, our own included, there lies a supermassive black hole, a region of space where matter has collapsed so completely that not even light can escape, weighing as much as millions or billions of suns compressed into a point. For most of a galaxy's life, this central black hole is quiet, or nearly so. It sits at the middle of everything, exerting its gravity, but not doing much that the rest of the galaxy would notice, a sleeping thing at the centre of a busy city, ignored by the traffic passing overhead. But there are times when a black hole feeds, and when a black hole feeds, it becomes one of the most violent things in the universe. When gas falls toward a black hole, it does not simply drop in. It swirls, forming a flattened, spinning disk of matter spiralling inward, and as that matter spirals down, it is compressed and heated by friction, and by the sheer ferocity of the gravity, heated to temperatures of millions of degrees, until it glows with a brilliance that can outshine every star in the surrounding galaxy combined. A feeding black hole at the centre of a galaxy is called an active galactic nucleus, and in its most extreme form, a quasar. It is the brightest steady thing in the entire cosmos, a beacon visible across the whole width of the universe, powered not by fusion like a star, but simply by the act of matter falling into a hole in space. It is worth pausing on how strange that is. The brightest objects in creation are powered by darkness, by the last glow of matter as it circles the drain of a place from which nothing returns. And here is the crucial thing, the thing that connects the feeding black hole to the death of its galaxy. All of that energy has to go somewhere. The radiation pouring off the glowing infell does not stay put. It floods outward into the galaxy, and it pushes. It heats the surrounding gas. It drives it. In the most violent mode, sometimes called the quasar mode or the wind mode, the black hole accretes so furiously that the radiation pressure launches galaxy-wide winds, streams of gas driven outward at hundreds of miles per second, and in the most extreme cases well over 1,000 miles per second, blasting through the galaxy's own reservoir of star-forming gas like a hurricane, tearing through a forest, stripping away the cool, dense material that stars need to form, flinging it out into the void where it can never gather and cool and collapse again. Think about what that does. Stars form from cold, dense gas. Gas that has gathered and cooled and grown heavy enough to collapse under its own weight. If you heat that gas, it puffs up and refuses to collapse, the way warm air rises and refuses to settle. And if you blow it out of the galaxy entirely, then there is simply nothing left to make stars from. The furnace does not just go cold, the fuel is thrown out of the house. Try to imagine forming snowflakes in a room where someone has turned on a blowtorch, and then imagine that the blowtorch is also strong enough to blast the windows out and scatter all the moisture in the air into the street. That is roughly what a feeding supermassive black hole does to the star-forming heart of its galaxy. It is called feedback, which is a mild and bloodless word for something so catastrophic, and it is the leading explanation for how galaxies die. It helps to sit for a moment with the sheer scale of the energy involved, because it is the energy that makes the whole thing work, and the numbers, once you feel them, explain why a single black hole can undo an entire galaxy. When matter falls toward a black hole and joins the glowing disk spiralling in, a substantial fraction of that matter's mass is converted directly into energy before it crosses the point of no return. This is far more efficient than the fusion that powers stars. A star like our Sun converts less than 1% of the mass it burns into energy. a black hole's accretion disk can release something closer to 1/10 of the infalling mass as pure radiation, more than 10 times as efficient as fusion, pouring it out as light and heat and pressure. So a black hole that swallows even a modest amount of gas each year releases an amount of energy that dwarfs the combined output of every star in the galaxy around it, and a galaxy is not, in the end, a very tightly bound thing. The gas that fills it, the raw material for future stars, is held only loosely by gravity, spread thin across tens of thousands of light years. It does not take an enormous fraction of a black hole's energy output to unbind that gas, to heat it past the point where it can cool and collapse, to push it up and out and away. In fact, only a small percentage of the energy a growing black hole releases, if it couples efficiently to the surrounding gas, is more than enough to sweep a galaxy clean. The black hole does not need to win by much. It only needs to release over the span of its feeding a little more energy than it takes to hold the galaxy's gas in place, and the gas loses, and the future of the galaxy goes out into the dark with it. The way that energy actually reaches the gas is through outflows, and this is where the measurements become vivid. The radiation and the winds from the black hole slam into the interstellar medium, the cool gas between the stars, and drive it outward in great expanding shells and streams. Astronomers measure the speed of these outflows by the shift in the colour of the light, and the speeds are staggering, hundreds of miles per second in the gentler cases, well over 1,000 miles per second in the most violent. A wind moving at 1,000 miles per second crosses the diameter of a compact galaxy in a few million years, and as it goes it sweeps the cool gas along with it, heating what it does not carry away, stirring the reservoir so thoroughly that nothing can settle and cool and collapse into a star. There is a number astronomers use to capture how destructive an outflow is, and it is called the mass loading factor. It is a simple ratio, the rate at which gas is leaving the galaxy divided by the rate at which the galaxy is still forming stars. A mass loading factor of 1 means the galaxy is losing gas exactly as fast as it is turning gas into stars. A rough balance. A mass loading factor much greater than 1 means the galaxy is hemorrhaging, losing its raw material far faster than it can ever use it, and no galaxy in that condition can survive. It is being emptied faster than it can build, and the arithmetic of that has only one ending. When astronomers measure mass loading factors well above 10 in these early dead galaxies, gas leaving more than 10 times faster than stars are forming, they are measuring a galaxy in the act of being scoured out, its fuel torn from it far faster than any process of star formation could ever consume it. There is a second mode as well, gentler in its violence but perhaps more lasting. In this mode, sometimes called the radio mode or the maintenance mode, the black hole launches narrow jets of plasma, beams of matter and energy shooting out from its poles at nearly the speed of light. These jets do not so much blast the galaxy's gas away, as heat the enormous halo of hot gas surrounding the galaxy, the reservoir from which fresh cool gas would normally rain down to fuel new star formation. By keeping that halo hot, the jets prevent the rain. No fresh gas falls in. The galaxy is not just emptied, it is prevented ever after from refilling. The furnace is not only extinguished, the chimney is sealed and the woodshed is set on fire, so that even the memory of fuel is denied. This is how a galaxy stays dead once it has died, how it resists the temptation to reignite even in a young universe awash with gas. The gentle mode is the one that keeps the grave from being disturbed. We do not have to imagine that black holes were doing this in the early dead galaxies. We can see the evidence written as always in the light. GS 9209, our old friend in the constellation of the Furnace, carries a startling clue. When astronomers measured the mass of its central black hole, they found something around 500 million to a billion suns worth of matter compressed into that central point. And that black hole was too big. Far too big. There is a well-established relationship in the nearby universe between the mass of a galaxy and the mass of the black hole at its centre, a proportion that holds remarkably steady across galaxy after galaxy, as though nature had settled on a fixed ratio between the size of a galaxy and the size of the monster at its heart. GS 9209's black hole was 4 or 5 times heavier than that relationship says it should be for a galaxy of its stellar mass. The man who found it called that a big surprise, and it is, because it suggests that in this galaxy the black hole grew first, grew fast, grew ahead of the galaxy around it, an engine racing far beyond the size of the vehicle it sat inside, a heart too large for the body it was meant to serve, and there is more. In GS 9209's spectrum, alongside the dead, cooling light of its aging stars, there was a faint but unmistakable signature of gas, moving at tremendous speed near the centre, a broad smear of hydrogen light so wide that it could only be produced by gas whirling around the black hole at velocities of thousands of miles per second, which means that even after the galaxy's star formation had completely stopped, even after the furnace had gone cold and the stars had begun their long slide into the red, the black hole at the centre was still feeding, still spinning up its disk of doomed gas, still glowing. The engine that killed the galaxy was still running long after the killing was done, idling in the dark at the centre of a corpse, a heart still beating in a body that had already gone cold. There is something almost unbearably lonely in that image, if you let yourself feel it. The galaxy dead all around, the stars all aging and reddening, and at the very centre, the thing that killed it, still turning, still glowing faintly, alone. There is another galaxy where we can watch the death happening even more directly, catch the murder practically in progress. It carries the cumbersome name SNH's PENS274, and it lives at an epoch when the universe was around 1.5 billion years old. This galaxy is caught in the act of quenching, still in the process of shutting down, and when astronomers looked at it they saw gas leaving, not gently. In the light of the galaxy were the signatures of iron and magnesium, and those signatures were shifted toward the blue, which is the fingerprint of material rushing toward us, flowing outward from the galaxy in our direction, at speeds of a couple of 100 miles per second. The gas was pouring out of the galaxy at a rate of around 20 suns worth of material every year, which was about 7 times faster than the galaxy was still managing to form stars. The galaxy was bleeding faster than it could heal. It was losing its raw material 7 times faster than it could turn that material into stars, and at that rate there could be only one outcome. The star formation rate collapsed from around 130 suns a year down to a mere 3, and it did so with a characteristic timescale of only about 50 million years. And here is the detail that made this galaxy so important to the astronomers who studied it. The gas was leaving as neutral gas, cool gas, precisely the kind of gas that stars are made from, traced not by the glow of hot ionized material, but by the shadow it cast, by the way it absorbed the light of the galaxy behind it in the lines of iron and magnesium. This was not the galaxy quietly running out of fuel and fading. This was ejective feedback, a term astronomers use for exactly this situation, the physical hurling of the star-forming gas up and out of the galaxy, the fuel not consumed but expelled, thrown out before it could ever be used. The galaxy was not starving, it was being emptied, and the outflow was carrying away far more gas each year than the galaxy was managing to turn into stars, which meant that even the fuel that remained was on borrowed time. In the language of the mass loading factor, this galaxy was losing badly, its outflow overwhelming its star formation, its reservoir draining faster than it could ever refill. Watching it was like watching a bath emptying while someone still stands at the tap trying to fill it, the water level dropping no matter how hard they run the faucet, because the drain is simply larger than the tap. The same story, told in the light of 2 galaxies separated by an enormous gulf of cosmic time, has now been read out in careful detail. Astronomers studying the outflows in recently quenched galaxies looked at one at an epoch when the universe was around 1.5 billion years old, and another from the extreme early universe, only 700 million years after the Big Bang, and in both of them they found gas fleeing, blue-shifted absorption in magnesium, the fingerprint of cool material streaming away toward us. In both, the mass loading factor was high, the outflow outrunning the star formation, and in both they reached the same uncomfortable conclusion. Supernovae alone, the explosions of dying massive stars, could not drive gas out fast enough to explain what they were seeing. The bookkeeping did not close. There was not enough energy in the stellar deaths to account for the fury of the outflow. Something else had to be pushing, something more powerful, something at the centre, an active black hole driving the wind even where the black hole itself lay hidden, too faint to see directly across those billions of light years. Two galaxies, one from the universe's first billion years and one from a bit later, telling the same story of gas expelled too fast for stars alone to blame, both pointing back to the same dark engine at the heart of the killing. 50 million years. To give that number a shape you can feel, consider that 50 million years ago on the Earth, the dinosaurs had already been gone for over 15 million years, and the first primitive ancestors of horses were small creatures no bigger than a dog, picking their way through warm forests that covered a world we would barely recognise. The entire rise of the mammals, the whole long story that leads eventually to us, fits inside the window it took this galaxy to go from a raging star factory to a nearly dead husk. On the scale of a galaxy's life, which runs to many billions of years, 50 million years is a slammed door. It is a heartbeat. It is death arriving not slowly, not gently, but all at once. In the span of time it takes a species to rise from a shrew to something that builds telescopes and points them at the sky. The most distant dead galaxy, the record holder from the universe's first 700 million years, shows the same violence. Astronomers detected gas streaming out of it too. Magnesium shifted toward the blue, material leaving the galaxy at more than 10 times the rate that stars were forming. And here is a subtlety worth pausing on, because it deepens the mystery rather than resolving it. There is a gentler way a galaxy can lose gas. When massive stars die, they explode as supernovae, and those explosions can drive gas outward, sweeping it up and pushing it away. But supernovae have a limit. They can only push so hard. And in this galaxy, the gas was leaving far too fast for supernovae to be the cause. Something more powerful was required. Something at the centre, blowing the galaxy apart faster than the stars themselves could ever manage. Most likely a black hole, feeding, driving its wind, tearing the galaxy open from the inside. And yet, in that particular galaxy, no black hole has been directly detected. Its light is too faint, too far, too old for us to see the engine itself. We see only the wreckage it leaves. We see the gas fleeing, and we infer from the speed of that flight the presence of a killer we cannot yet lay eyes on. It is like arriving at a scene where the doors are blown off their hinges and the dust is still settling in the air, and knowing that something powerful was here and just left, and finding no other trace of it at all. There is a further wrinkle here, one that tells us these winds may not have been a single event, but a series of them, a slow and episodic execution rather than one clean blow. When astronomers look at the outflows in these recently quenched galaxies, at the gas still streaming away from them, the pattern often looks less like the aftermath of one great blast and more like the relic of several. The black hole, it seems, does not fire once and fall silent. It flickers on and off, feeding in bursts, driving a wind, going quiet, feeding again, driving another wind, over and over, each cycle stripping away a little more of the galaxy's ability to make stars. And there is evidence that these winds can persist, that the high-speed gas driven out by an ancient burst can go on fleeing the galaxy for hundreds of millions of years after the burst that launched it has ended, a long exhalation that outlasts the breath that started it. So the death of one of these galaxies may not have been a moment at all. It may have been a slow strangulation, spread across 100 million years or more, the black hole waking and feeding and sleeping and waking again, each waking taking a little more of the galaxy's future, until at last there was nothing left to burn and the whole thing went dark for good. This is a recurring theme in the study of the early dead galaxies. When astronomers examined a set of 14 of the most massive dead galaxies from these early epochs, They found that around half of them showed some sign of a black hole still active at the centre, some faint fingerprint of a lingering engine. Half. That is a striking fraction for galaxies that have supposedly finished their main work, stopped their star formation, gone quiet. It suggests that the black hole does not switch off when the galaxy dies. It lingers, it idles, it goes on feeding and glowing in the dark long after the stars around it have begun to cool. The last light in a darkening house, the one window that stays lit after everyone has gone to bed and the rest of the street has fallen dark. And it deepens the sense, as you lie there in the dark, that these galaxies did not simply fade away. They were killed. Something at the centre of each one grew too large, too fast, fed too furiously, and in feeding poured out enough energy to blast away or heat away or seal away the very gas the galaxy needed to go on living. They lived fast, in a single, furious burst of creation. They died young, cut down in 100 million years or less. And the thing that killed them was, in most cases, the black hole they had grown at their own heart, a monster nurtured in the galaxy's own gut that turned, when it grew large enough, and devoured the future of the thing that made it. There is an old and terrible symmetry in that. The galaxies built the very thing that would end them, fed it and grew it and gave it a home at their centre, and it repaid them by taking away their ability to make anything new ever again. But here is where the puzzle folds back on itself, because there is one dead galaxy that this whole explanation does not fit, and it is the small one, the quenched dwarf from the first 700 million years. That galaxy is far too small to have the kind of monstrous black hole that drives these galaxy-wide winds. It holds only a few 100 million suns, tiny by any standard, and the physics of black hole feedback is supposed to matter only for the giants. And yet it died too. It went silent too, all its bright lines flat, all its star formation stopped. Something shut it off, and whatever that something was, it was not the same monster that killed the giants. Maybe the little galaxy was stripped of its gas by falling through a denser region, its fuel torn away by forces outside itself. Maybe it simply exhausted its fuel in one brief burst and paused, holding its breath, waiting to be born again in some future we cannot watch. Maybe there is a way to kill a small galaxy that we have not yet mapped, a mechanism operating quietly in the low-mass dark. We do not know. It sits there in the data, dead and small and inexplicable. A footnote that refuses to be footnoted. A small dark reminder that even our best explanation for how galaxies die does not cover every corpse in the graveyard. Tonight, we're going to look, at last, at what all of this means for the rulebook itself. Now let your mind drift back for a moment to the sharpest edge of all this, the thing that makes the dead galaxies more than a curiosity, the thing that presses on the foundations. It is the collision between what these galaxies are and what our theory says they can be, because the tension is real, and it is worth understanding what exactly is at stake and what is not, before you let the whole thing dissolve into sleep. Lambda CDM, the standard model of cosmology, is not in danger of collapse. Let me be very clear about that, because it would be easy, in the dark, to slide into thinking that Webb has broken the universe, that the foundations have cracked and the whole edifice is coming down. They have not. The great successes of the theory stand. The afterglow of the Big Bang still matches its predictions to exquisite precision. The cosmic web still hangs in the sky exactly as it should. The dark matter framework, that scaffolding of invisible mass on which the whole luminous universe is draped, appears to be intact. What is failing is something more specific and, in a way, more human. What is failing is our model of the messy, complicated, small-scale physics of how galaxies actually form inside that scaffolding, how gas cools, how stars ignite, how black holes grow, how feedback works. This is the part of the theory that we do not derive from first principles, but instead stitch together from approximations, Rules of thumb, best guesses about physics too complicated to compute directly. Astronomers call it the subgrid physics, the physics that happens below the resolution of the simulation, the physics we have to fake because the real thing is too intricate to compute. And it is the subgrid physics, not the dark matter, that the dead galaxies seem to be breaking, which is, in its way, reassuring. It means we probably do not need to tear down the whole edifice. It means the answer may lie in fixing our recipe for how galaxies grow and die, rather than in discovering that the universe is made of something other than what we thought. And there is a hopeful sign that this is the right direction. There is a newer simulation, one of the most recent and sophisticated yet built, and unlike its predecessors, it does something the others refuse to do. It lets its black holes eat too fast. There is a limit, in principle, to how fast a black hole can feed. It is called the Eddington limit, and the idea behind it is elegant. As a black hole feeds, the infalling matter glows, and that glow exerts an outward pressure. Feed too fast, and the outward pressure of the radiation should overwhelm the inward pull of gravity and choke off the flow. Like a fire that burns so hot it blows itself out, starving itself of the very air it needs. The Eddington limit is the point where those two forces balance, the theoretical maximum feeding rate, the speed limit written into the physics of falling matter. Most of the older simulations refused to let their black holes exceed it. They capped the feeding at Eddington, playing it safe, respecting the classical limit. And with that cap in place, their black holes grew slowly, and their feedback came late and gentle, and their galaxies stubbornly refused to die early. The cautious simulations produced a cautious universe, and the cautious universe had no early dead galaxies in it. The newer simulation, called COLIBRE, throws off the cap. It allows its black holes to feed beyond the Eddington limit, to gorge in brief violent phases, faster than the classical physics says they should be able to. Super-Eddington accretion, it is called, a black hole eating past its own speed limit. And in that simulation, around half of all the black hole growth at early times happens in this super-Eddington regime. Black holes eating faster than the rules allow, growing enormous with startling speed, and then, when they grow large enough, pouring out enough energy to quench their galaxies early and hard. And when you count the dead galaxies in this super-Eddington universe, you find, for the first time, roughly the right number. The simulation that lets its black holes cheat is the simulation that finally matches the real sky. The universe, it turns out, was cheating all along, and we had simply refused to let our models do the same. It is worth being precise about why the older simulations forbade this, because the prohibition was not arbitrary. The Eddington limit is a genuine piece of physics, and for a black hole feeding in a calm, steady, spherical way, it holds. But the early universe was not calm or steady or spherical. Gas came pouring into the centres of these young galaxies in dense, turbulent, lopsided floods, far more gas than a tidy spherical model assumes. And when gas is dense enough and falls fast enough, the radiation that would normally push back and enforce the limit can become trapped, buried in the infalling material, unable to escape and do its job of throttling the flow. The black hole, shielded from its own light, can go on gorging past the point where the simple limit says it should choke. This is super-Eddington accretion, and it is not really a violation of physics so much as a regime the simple limit was never meant to cover. The physics of a black hole eating in a flood rather than a trickle. The older simulations, built and calibrated in the Tamer-late universe, simply capped their black holes at the classical limit and never let them enter this regime, because in the late universe the regime rarely matters. In the early universe, it may have mattered enormously. It may have been the whole story. And when COLIBRE lets its black holes enter that regime, when it allows them to gorge in floods rather than sip in trickles, the consequence cascades through everything. The black holes grow enormous far faster, reaching hundreds of millions of solar masses, while the universe is still young, which is exactly what GS 9209's oversized central black hole seemed to demand. and a black hole that large, feeding that hard, pours out enough energy early enough to blast its galaxy clear of gas and shut it down within the first billion years, which is exactly what the graveyard of dead galaxies demands. One change to one handwritten rule, letting the black holes eat past the old cap, and the simulated universe suddenly grows, the same corpses the real universe is full of. It is a striking demonstration that the whole mystery may live in that one prescription, that we were not wrong about the shape of the cosmos, but only about the appetite of the monsters at the centres of its first great galaxies. There is a lesson in that, and it is a lesson you can carry gently into sleep. For years we built simulations that were careful, that respected the classical limits, that assumed the universe would not do anything too extreme. And the universe, it turns out, was more extreme than we allowed it to be. It grew black holes faster than we thought possible. It quenched galaxies earlier and harder than we imagined. It lived fast and it died young in ways our cautious models could not reproduce, precisely because our models were too cautious. The dead galaxies are not telling us that physics is broken. They are telling us that the early universe was wilder than we dared to simulate, and that we underestimated the ferocity of its youth. We built a calm and orderly childhood for the cosmos, and the cosmos, when we finally looked, turned out to have had a wild one. There is another idea worth mentioning, quieter and more uncertain, a loophole that might make part of the mystery smaller. When astronomers measure the mass of a distant galaxy, they cannot count its stars one by one. They measure how much light it gives off, and they work backward, using their knowledge of how much light a star of a given mass produces. But to do that, they have to assume something about the mix of stars. How many small dim stars are there for every large bright one? This mix is called the initial mass function, and near us, it seems to hold fairly steady. The same recipe of small and large stars showing up again and again. But what if, in the early universe, the mix was different? What if the first galaxies made more massive bright stars and fewer small dim ones? Then the same amount of light would come from fewer total stars, and the galaxies would weigh less than we think. Some of the tension might ease. The impossibly heavy galaxies might turn out to be merely very heavy, still surprising, but not quite impossible. This idea is debated, unresolved, neither proven nor ruled out. It is one of several threads researchers are pulling, hoping that one of them, when tugged, will unravel the knot. But even the astronomers who propose these fixes tend to admit that none of them alone seems quite enough. The galaxies are stubbornly, genuinely strange, and no single easy answer has yet made them ordinary. And there is one more revival worth mentioning, an old idea that these galaxies have called back from the dead, which is a fitting thing for dead galaxies to do. Long ago, before the hierarchical picture won the day, some astronomers favoured a different story about how big galaxies form. They called it monolithic collapse, and it imagined that a giant galaxy formed not from the slow merging of small pieces, but all at once, in a single vast collapse of an enormous cloud of gas, igniting hundreds of stars a year across its whole volume simultaneously, blazing for a couple of 100 million years, and then going dark. This idea fell out of favour in the 1990s, when the hierarchical bottom-up picture proved so successful at explaining the universe near us. It was set aside, filed away as a scenario that had lost. But the early dead galaxies look, in many ways, exactly like what monolithic collapse would produce. A single, furious burst, a compact, dense result, a rapid death. The astronomer who studied GS 9209 said that for that galaxy at least, monolithic collapse now looks like what actually happened, that it may be the clearest proof yet that galaxies can form that way. An old idea, buried for 30 years, quietly reanimated by the corpses of galaxies 12 billion years dead. There is a symmetry in that which is almost too neat to be true, and yet there it is, waiting in the data. Perhaps the monolithic collapse and the black hole feedback are two halves of a single story. Perhaps a giant cloud collapses all at once, and that violent collapse funnels an enormous concentration of gas into the centre, feeding the black hole there to super-Eddington rates, growing it huge with terrifying speed until the black hole grows large enough to blast the whole galaxy clear of its gas and shut it down before it can merge with anything or grow any further. One vast birth and a swift self-inflicted death. Born in fire, killed by the fire's own heart. If that sequence is right, then these galaxies are not really a contradiction of lambda CDM at all. They are a chapter of it we had simply failed to imagine, a way for the universe to build and destroy a great galaxy in the space of a few 100 million years that we were too cautious to write into our models. The rulebook was not wrong. We had just not read all the way to the end of it. Tonight we're going to leave the theory behind for a while and simply visit these places as places. Let your mind rest for a moment on the sheer strangeness of these objects, considered not as problems for theory, but simply as places. Because that is what they are. They are places. They existed. They were real. And in some sense, transformed and grown, they may still be out there, hidden inside the galaxies of today, carried forward across all of cosmic time. Consider what it would have been like inside ZF-UDS 7329, the relic galaxy whose stars brush the age of the universe. The stars inside it move at extraordinary speeds. The astronomers measured the velocity dispersion, the average speed at which its stars whirl around inside it, and found it to be around 155 miles per second, meaning the typical star inside the galaxy hurtles through space at over 500,000 miles per hour. In our own Milky Way, the stars move at less than half that speed. These early dead galaxies are not only small and old and dense, they are dynamically ferocious, their stars packed tight and moving fast, whole populations of suns whipping around a common centre at velocities that would beggar any intuition built on the calm, slow, spread-out galaxy we live in. One of the other early dead galaxies has stars moving even faster, averaging over 800,000 miles per hour. To stand inside such a place, if you could survive it, would be to stand in a swarm of suns, all of them ancient, all of them red, all of them tearing past you in the dark at speeds that turn a human lifetime into nothing. A place both very old and very fast, both a graveyard and a storm, silent and furious at once. And these galaxies, the astronomers believe, did not simply vanish. They grew. Over the 12 billion years that followed their death, they went on colliding and merging with other galaxies, but with a difference. They had no gas left, no fuel, so their mergers made no new stars. Astronomers call these dry mergers, collisions of gas-poor, star-dead galaxies that simply fold their old stars together into ever larger structures without lighting a single new flame. Through these dry mergers, spread over eons, the compact dead galaxies of the early universe are thought to have grown into the giant elliptical galaxies we see today. The vast, featureless, reddish spheres of old stars that sit enthroned at the centres of the great galaxy clusters, the largest galaxies in the modern universe. If that is right, then the corpses we are studying are not really gone. They are the seeds, the ancient hearts, buried now inside the largest galaxies in creation. Their oldest stars still there, still red, still moving fast, still carrying the memory of a burst of creation that happened when the universe was less than 1 billion years old. When you look at a giant elliptical galaxy today, a great smooth crimson sphere at the heart of a cluster, you may be looking at a body that grew across all of cosmic time around a core that was already dead when the universe was young, a modern giant with a very old ghost at its centre. Let that settle. The dead did not stay small and forgotten. They grew into giants, and their descendants are among the grandest structures in the sky. The great red kings at the centres of clusters, each one perhaps holding deep in its heart the ancient dead thing that started it all. There is so much still unknown, and it is worth dwelling in the unknown for a while, because the unknown is a soft place and a good place to drift. We do not know for certain whether the black hole is always the killer. We do not know how the smallest dead galaxies died. We do not know whether the gas that these galaxies blew out into the void ever fell back, or whether it escaped forever into the thin, cold medium between the galaxies, scattered beyond recovery. We do not know why the black holes in these early galaxies grew so much faster and larger than the ones we see near us, racing ahead of their host galaxies in a way that violates the tidy proportions of the modern universe. We do not know whether a small revision to the mix of stars might ease the tension, or whether the tension is telling us something deeper about the physics of the early cosmos. We do not know how many more of these galaxies are out there, fainter and earlier and stranger, sitting just beyond the reach of even Webb's long exposures, waiting, as GS 9209 waited for 20 years, for an instrument that has not yet been built, a telescope that no one has yet imagined. We do not even know, in the end, exactly what these galaxies looked like from the inside, what their skies would have shown, what it would have felt like to drift through their crowded, ancient, reddening light. We can only read their spectra, the thin threads of information that survive the journey across 12 billion years and more, and from those threads reconstruct carefully and humbly the outline of a story. Everything else is inference and imagination, and the honest admission that most of what happened out there, in the deep past in the young universe, we will never fully know. And there is a strange comfort in that too, a comfort worth carrying towards sleep. The universe keeps most of its story to itself. We catch only fragments, and even the fragments are enough to fill a mind with wonder for a lifetime. What we do know is that the story we told ourselves about the early universe was too gentle. We imagined a slow dawn, a patient assembly, a universe taking its time, and the real universe, it turns out, came roaring out of its dark ages, building giant galaxies in furious bursts, growing monstrous black holes at super-Eddington rates, quenching whole galaxies in the span of 50 or 100 million years, and leaving behind a graveyard of the dead. No one predicts a universe that finishes its greatest galaxies and buries them in its first billion years, and yet that is the universe Webb has shown us, corpse by corpse, spectrum by spectrum. The model said the fires should all still be burning. Webb opened its eye and found that some of them had already gone out, long ago, at the very dawn of time, and there is a final image worth carrying with you into sleep, one that ties the whole night together. Every one of these galaxies, GS 9209 in the furnace, the record holder from the universe's first 700 million years, the relic whose stars are nearly as old as time, the small, strange quenched dwarf, all of them are sending us their light right now, tonight, and have been sending it for billions of years, and will go on sending it for billions more. The light we caught is only the light that happened to arrive during the brief window of a human lifetime. The rest is still coming. It has been in flight since before the Earth, and it will still be arriving long after the Earth is gone, streaming across the widening dark, carrying the news of ancient deaths to whoever or whatever is there to catch it. These galaxies died a very long time ago, in a universe very young, but their light does not know that. Their light is patient. It simply travels and travels and travels, and one night, after 12.5 billion years, a little of it falls into a golden mirror a million miles from a small blue world, and a quiet person in a quiet room reads, in the pattern of that light, the story of a fire that went out at the dawn of time. That is the whole strange grace of astronomy. Everything we see out there has already happened. The sky is a museum of the past, and the further you look, the older the exhibits, until at last, near the very edge of what we can see, you find the graveyard of the first galaxies, the ones that lived fast and died young, and you realize that the universe has been keeping the secret in plain sight for the whole of human history, and only now, only in the last few years, have we finally learned how to read the epitaphs. The stones were always there. We simply lack the light to see the writing on them. So as you lie there, drifting now, let the galaxies keep you company. They are very old, and they are very quiet, and there is nothing you can do for them, and nothing they can do to you. They asked for nothing and they need nothing. They simply lived and burned and died a long time ago in the young universe, and their light goes on, arriving in the dark whether anyone is awake to read it or not. There is no urgency in them. There is no worry in them. There is only the long, slow, patient fact of their existence and their death, and the light still crossing the void to tell us of it. Let that patience settle over you like a blanket. Let it slow your breathing. There is nowhere to be, and nothing to finish, and all the time in the world. Tonight we explored what it means for a galaxy to die, the silence in the spectrum where the bright lines of life should be, the sharp cliff of the Balmer break, the deep dark hydrogen lines that mark a fire recently gone cold, and we sat with GS 9209 in the constellation of the Furnace, 40 billion suns packed into a space 60 times smaller than the Milky Way, already old and cooling before our own sun was born, its black hole still idling faintly at the centre of a corpse. Tonight we followed the long patient road of the discovery, the 20 years these red smudges waited in Hubble's catalogues, too faint and too red for any telescope on the ground to read, until a folded golden mirror unfurled 1,000,000 miles from home and finally caught their ancient light, and we met the whole graveyard behind them, the record holders and the relics and the small strange quenched things, 225 of them in a patch of sky the size of 2 full moons, a whole cemetery hidden in plain sight for the length of human history. And tonight we sat inside the deepest question of all, how a galaxy dies so young and so completely and so early, the monstrous black holes feeding faster than the rules allow, the winds tearing the star-forming gas out into the void at hundreds of thousands of miles per hour, the simulations that found almost none of these galaxies while the real sky's full of them, and the slow, humbling lesson that the early universe was wilder and fiercer and faster than we ever dared to let our models be. There is nothing left for you to do tonight. The galaxies are dead, and have been dead for longer than the Earth has existed, and their light will go on arriving in the dark long after this night is over. You can let all of it go now. Let the numbers fall away. Let the names dissolve. Keep only, if you keep anything, the soft image of a faint red light, very old and very far, falling at last into a golden mirror in the cold beyond the moon, carrying the quiet news that something out there lived and burned and died at the very dawn of time, and that we, against all odds, finally learned how to read it. Sleep well tonight. The universe has been keeping its secrets for nearly 14 billion years, and it will keep them